Jai Hind everyone, I am from Indian Space Team Rocket Science Division. Have you ever wondered how hybrid rocket engines work? Well, you're about to find out. Hybrid rocket engines are a type of rocket propulsion system that combines elements from both solid and liquid rocket engines. They're a bit like a culinary fusion, blending the best of both worlds to create something new and exciting. These engines use a solid fuel and a liquid or gaseous oxidizer, a mix that allows them to achieve a balance between the high efficiency of liquid engines and the simplicity and safety of solid engines. They're not as common as their solid and liquid counterparts, but they're starting to gain traction in the world of rocket science, particularly in areas where safety, cost, and flexibility are key considerations. Now that you have a basic understanding of what a hybrid rocket engine is, let's delve deeper into how they work. So what fuels a hybrid rocket engine? When it comes to hybrid rocket engines, the fuel choices are diverse and fascinating. The most common fuels include polymers and liquefying fuels. Polymers like acrylics and polyethylene are used due to their availability and effectiveness. Cross-linked rubber, such as hydroxyl-terminated polybutadiene, HTPB, is another popular choice. But why stop at polymers? Liquefying fuels like paraffin wax also play a significant role. Plexiglass was once a common fuel, mainly because the combustion process could be observed through the transparent combustion chamber, adding a dash of visual drama to the scientific spectacle. However, the star of the show is undoubtedly HTPB synthetic rubber. It's currently the most popular fuel for hybrid rocket engines, and for good reasons. HTPB stands out due to its energy output and its safety. In fact, tests have shown that even when soaked in liquid oxygen, HTPB does not become explosive. Safety first, right? That being said, these fuels are generally not as dense as those used in solid rocket motors. To improve the rocket's performance, they are often doped with aluminum to increase the density. Now there's a twist in the tale. Have you heard of reverse hybrid rockets? They are not very common, but they use a solid oxidizer and a liquid fuel. Some of the liquid fuel options include kerosene, hydrazine, and LH2. Despite being less common, they offer an interesting alternative view on the possibilities of rocket fuel. So, as you can see, the world of hybrid rocket fuels is a diverse one, with each fuel bringing its own unique characteristics to the table. The choice of fuel depends on various factors, including the specific requirements of the rocket and the safety considerations. Next, we'll discover how these fuels are prepared for use in a hybrid rocket engine. And trust me, it's a process as fascinating as the fuels themselves. Stay tuned. Before being used as fuel, these materials need to be processed. But how? Well, it's all about the grain manufacturing methods. There are two main techniques to manufacture hybrid rocket fuel grains: casting and additive manufacturing. Let's start with casting. It's an age-old technique and quite popular too. Hybrid rocket fuel grains, typically being plastic or rubber, are well suited for this method. Casting allows for the creation of complex geometries driven by the need for higher fuel mass flow rates. However, casting fuel grains for hybrid rockets can be expensive and time-consuming, primarily due to equipment costs. Also, when we're talking about large-scale grains, they need to be supported by internal webbing to prevent large chunks of fuel from potentially blocking the nozzle. And let's not forget about grain defects, which can be an issue in larger grains. Traditional fuels that are cast include hydroxyl-terminated polybutadiene, also known as HTPB, and paraffin waxes. On the other hand, additive manufacturing, also known as 3D printing, is a newer and increasingly popular method. It can create grain structures that were otherwise not possible to manufacture. One example is helical ports, which have been shown to increase fuel regression rates while also increasing volumetric efficiency. The material commonly used for a hybrid rocket fuel in this method is acrylonitrile butadiene styrene, or ABS. The printed material is typically enhanced with additives to improve rocket performance. Recent work has shown that, due to the increased surface area, the use of powdered fuels encased in a 3D printed ABS matrix can significantly increase the fuel burn rate and thrust level as compared to traditional polymer grains. So there you have it. Whether it's the time-tested casting or the innovative additive manufacturing, each method has its unique process, advantages and disadvantages. It's fascinating how these materials are processed and prepared to be used as fuel in hybrid rocket engines. With our fuel ready, we now need something to ignite it. Let's talk about oxidizers. An oxidizer is crucial to ignite the fuel, but what are the common choices? Let's dive into the world of oxidizers, the unsung heroes of rocket propulsion. These substances provide the oxygen that fuels need to burn and propel us into the cosmos. The common choices for oxidizers in hybrid rocket engines include gaseous or liquid oxygen, nitrous oxide, and hydrogen peroxide. Each of these substances plays a pivotal role in the combustion process, but they also bring their unique characteristics to the table. Gaseous or liquid oxygen, for instance, is a potent and reliable oxidizer. It's a classic choice, having powered countless rockets since the dawn of the space age. Nitrous oxide, on the other hand, is a bit of an upstart. It's not as powerful as oxygen, but it's safer to handle and store, making it an attractive choice for certain applications. And then there's hydrogen peroxide, a versatile substance that can act as an oxidizer, a monopropellant, or even a coolant in some cases. Now, it's not enough to simply have an oxidizer. It has to be vaporized properly. Why, you ask? Well, proper vaporization ensures that the oxidizer mixes thoroughly with the fuel. This leads to a more efficient and controlled burn, which in turn results in better rocket performance. Improper vaporization, however, can lead to significant regression rate differences at the head end of the motor when compared to the aft end. This can cause all sorts of problems, from reduced thrust to instability. So how do we ensure proper vaporization? One method is to use a hot gas generator to heat the oxidizer in a pre-combustion chamber. Another method is to use an oxidizer that can also be used as a monopropellant, like hydrogen peroxide. In this case, the oxidizer can be decomposed over a silver bed into hot oxygen and steam, which ensures proper vaporization. In the end, the choice of oxidizer and the method of its vaporization are crucial to the performance and safety of a hybrid rocket engine. Now that we have our fuel and oxidizer, let's talk about safety. Safety is paramount when dealing with rocket engines, but how safe are hybrid rocket engines? Let's delve into the world of hybrid rocket engines and their safety features. Among the many types of rocket engines, hybrid engines are known for their inherent safety. This is largely due to the physical separation of fuel and the oxidizer until the moment of ignition. This separation decreases the likelihood of accidental ignition, making these engines safer to handle, store, and transport. One of the primary hazards associated with hybrid rocket engines is pressure vessel failures. These can occur if the chamber insulation fails, allowing hot combustion gases to come into contact with the chamber walls. This can lead to a burn-through where the chamber walls are breached by the intense heat. It's a bit like a pressure cooker going awry, but on a much larger and more dangerous scale. However, this is a rare occurrence and can be largely mitigated with careful design and construction. In addition to meticulous design, the choice of materials used in hybrid rocket engines also contributes to their safety. For instance, hydroxyl-terminated polybutadiene, or HTPB, is a synthetic rubber that's a popular fuel choice for these engines. It's not only energy-dense, but also remarkably safe to handle. Tests have shown that even when soaked in liquid oxygen, it doesn't become explosive. That's a testament to the safety margin built into these engines. Moreover, the manufacturing methods for creating fuel grains, such as casting techniques or additive manufacturing, also allow for complex geometries that enhance safety. For instance, internal webbing can prevent large chunks of fuel from blocking the nozzle, while innovative grain structures can increase fuel burn rate and thrust level, improving overall engine performance and safety. So, while hybrid rocket engines are complex pieces of engineering, they are designed with safety as a top priority. With careful design, construction, and operation, these engines can be safely used for a variety of applications, from space exploration to scientific research. That wraps up our discussion on the workings of hybrid rocket engines. Let's quickly recap what we've learned today. We've delved into the captivating world of hybrid rocket engines. We've discovered that they operate using a variety of fuel choices, with polymers like acrylics, polyethylene, cross-linked rubber, and liquefying fuels such as paraffin wax being common options. We also highlighted the popularity of hydroxyl-terminated polybutadiene synthetic rubber due to its energy and safe handling properties. We explored the intricacies of grain manufacturing methods, including casting techniques, and the potential use of additive manufacturing to create complex grain structures. We also discussed the use of powdered fuels encased in a 3D printed matrix to increase fuel burn rate and thrust level. We then delved into common oxidizer choices, emphasizing the importance of proper oxidizer vaporization for efficient rocket performance, with common options being gaseous or liquid oxygen, nitrous oxide, and hydrogen peroxide. Thank you for joining us on this fascinating journey into the world of hybrid rocket engines. Until next time, keep exploring.